Okay, now we move on to energy and power. Energy and power are the natural building blocks in moving from voltage, current, and resistance. So we're going to see how we use voltage, current, and resistance to build our units of energy and power. So in this section, we're going to look at power and electric circuits, resistor, power ratings, the energy conversion and voltage drop and resistance, and power supplies and battery. Using those to define energy and power, calculating the power in a circuit, selecting resistors of the proper values based on power, explaining energy conversion and voltage drop, and power supplies and their characteristics. So we've got some new terms we've got to get used to. So we've gotten used to voltage, current, and resistance, voltage, amps, and ohms. Now we need to look at energy, power, the unit of joules, watts, a kilowatt hour, notice that's a product, voltage drop, ampere hour, rating, again a product, and efficiency. So we're going to be looking at, for our objectives, building all of these key terms and key concepts so that we can better understand them. When there's current through a resistance, electrical energy is converted to heat or other forms of energy, such as light. A common example of this is a light bulb that becomes too hot to touch. The current through the filament that produces light also produces unwanted heat because the filament has resistance. Electrical components must be able to dissipate a certain amount of energy in a given period of time. So we're going to look at, as we move forward, how we look at resistance and current and the loss that occurs in a circuit. Heat is always a very detrimental function in a circuit. Heat kills. So unless we're dealing with a device like a light bulb that we want it to heat up so that it creates light, heat in a circuit is not a good thing. So we will look at how we rate our devices so that we can understand with power and energy what is actually going on here in terms of use of current and energy. Energy is then the ability to do work. So you need to be thinking synonymously, energy and work. Energy and work are the same thing. And power then is a rate. So with power, we always take work or energy, divide it by time to make it a rate. So its power is the rate at which energy is used. Power is a certain amount of energy used over a given or certain length of time, expressed as follows. So power, P, is equal to work divided by time. Okay, so there's our definition. Note that an italic W is used to represent energy in the form of work. A non-italic W is used for watts. So we're starting to look at overlaps in our symbology, so we have to be careful and understand every time we use our units, and we should be using units on every function that we put down. Unless it is a unitless number, we should be including our units. So italic W for work, non-italic for watts. Okay, so that's power, that's energy. Okay, the joule, a capital J, is the SI unit for energy. Later we're going to find out that a little j is something that we use for complex numbers. Energy in joules then divided by time in seconds gives us power in watts. Okay, so you should be writing this down in your notebook. Every time you come up with a new concept or a new definition, you should be writing it down so that you have it handy, so that you can keep proving to yourself what these units really mean. So for example, if I have 50 joules of energy used in 2 seconds, 50 joules divided by 2 seconds gives me 25 watts, okay, of power. So by definition, we normalize things and tie everything to a value of 1 occasionally. 1 watt is the amount of power when 1 joule of energy is used in 1 second. So notice all the ones. It normalizes everything. Thus, the number of joules used in 1 second is always equal to the number of watts. So for example, if we have 75 joules used in 1 second, the power then becomes 75 joules per second. So a joule per second is a watt. So now we can see we've got a way that we can manipulate values further on when we have to start doing conversions. Amounts of power much less than 1 watt, though, are common in certain areas of electronics. Typically, we use tiny values of wattage in electronic circuits. In electrical circuits, like power generating devices, of course, we use the larger designations. As with small current and voltage value, metric prefixes then are used to designate small amounts of power. Thus, milliwatts, little m, capital W, microwatts, little mu, capital W, and even picowatts, little p, capital W, are commonly found in some applications. In the electrical utilities field, though, kilowatts, thousands of watts, and megawatts, millions of watts, are common units. Radio and television stations also use large amounts of power to transmit signals. So this is your larger megawatt signals. Electric motors then are commonly rated in horsepower, where 1 horsepower is 746 watts. Okay, and that's something you'll need to learn for conversions. Since power is the rate at which energy is used, as expressed in equation 4.1, power utilized over a period of time represents energy consumption. If you multiply power in watts and time in seconds, you have energy in joules, symbolized by the italic W. So there's your representation there, okay? Let's look at an example. An amount of energy equal to 100 joules is used in 5 seconds. What is the power in watts? So energy over time, W over T, 100 joules, 5 seconds. Joules per second is a watt. We have 20 watts. Okay, you work the related problem. The next one, express the following values of electrical power using appropriate metric prefixes. As I said, you've got to be used to using these metric prefixes and moving back and forth between the exponential relationships and the metric relationships. So 0.045 watts is equal to 45 milliwatts. Why is that so? Well, if we take the decimal place and move it 1, 2, 3, that becomes the milli portion, and now this becomes 45 milliwatts. 12 with 4 zeros in front of it, 0.0000012. So let's look at this. Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, okay, and so on. So what we're looking at is 12 microwatts in this case. What did we do? We took the decimal place and we moved it 6 places. 1, 2, 3, 4, 5, 6 places. Now we have the whole number 12. We add the micro for 10 to the minus 6 watts. 3,500 watts. 3,500 watts becomes 3.5 kilowatts. I took the understood decimal point right here, moved it 1, 2, 3 places. I get 3.5 kilowatts. In this case, 10 million watts. So this one is pretty easy. You can see we have 6 zeros. 6 zeros is 10 to the 6. 10 to the 6 is mega. So I have 10 megawatts. Okay, so practice doing those. Again, pull out your notebook, write these down, prove to yourself that they in fact work and what your metric versus exponentials relate to in solving these types of problems. So we've looked at energy and power and defined energy measured in joules, time measured in seconds, power measured in watts. If we solve for 50 joules divided by 2 seconds, so that's 50 joules of energy over 2 seconds, we get 25 watts. Okay, so in the next video we'll talk about the kilowatt hour and the units of energy in something like the utilities industry.